and it's a pleasure to welcome you to the IDA National Renewable Energy Laboratory Teaming Webinar. This initiative is part of the U.S. Department of Energy American-Made Challenge for the Solar Desalination Prize. The challenge is a 4-stage competition designed to accelerate the development of low-cost desalination systems that use solar power to produce clean water from saltwater. Competitors receive cash prizes as they advance through each stage of the competition, culminating in a $1 million grand prize for the successful testing and demonstration of a promising solar thermal desalination system prototype. This morning, each of the 19 innovation phase winners will make a short 4-minute pitch about their project. There will be 1 speaker per team. IDA has sent all participants the team's contact information so that after this session, you may be in direct contact with them. We are delighted to organize this innovative session to support the 19 quarterfinalists in the teaming phase, which challenges them to take their preliminary concept into a fully operational prototype and further build their teams. For those of you who are not already members of the IDA is a nonprofit and international membership organization established in the United States with recognition from the United Nations. For over 45 years, the association has served as a global hub for the worldwide desalination and water reuse industry. The IDA mission is to promote sustainable practices in desalination, water reuse, and recycling. And the IDA has committed to advocating an H2O minus CO2 approach to reduce the CO2 footprint in these advanced water treatment systems through the incorporation of renewable energy to power both large and small scale systems on-grid and off-grid to meet water needs. With only 3% of the world's water being fresh and over 70% of that being frozen, global freshwater availability is under stress. Global water demand is expected to increase by 20 to 30% above the current level of water use by 2050. Desalination and water reuse have increasingly become a viable option to close the water gap. Energy is a critical factor in the cost equation of desalination and the transport of the desalinated water. However, currently, of the total installed capacity worldwide, only 1% of the desalination facilities use solar power. We all know that it is the energy source that will be the ultimate game changer in lowering desalination cost. So enabling a sustainable future requires desalination to be coupled with renewable energy, primarily solar and wind. IDA applauds the US Department of Energy, the US National Laboratories, and all the universities and research teams involved in the Solar Desalination Challenge. We are very pleased to present them to the IDA community this morning. Without further ado, I now invite Daniel Zimny-Schmidt, an energy and mobilities researcher at NREL, to give his welcome remark, followed by our distinguished moderator, Professor John H. Leinhard V, who is the Abdul Latif Jamil Professor of Water and Mechanical Engineering at MIT and an officer of the IDA Board of Directors, serving as Dean of the IDA Academy. Daniel?
Yes, good morning, everyone. Thank you for being here today. My name is Daniel Zimny-Schmidt, and I work at the National Renewable Energy Lab, which is currently host to a variety of prizes and challenges designed to stimulate American entrepreneurship and innovation. Today, we're here to hear from the 19 quarterfinalists of the Solar Desalination Prize, whose ideas have attracted the interest of both the Department of Energy and an independent panel of reviewers. These teams have been selected from an initial pool of more than 160 submissions to earn their space in this second round of 4 in the Solar Desalination Prize. The goal of this prize competition is for teams to fully develop their ideas all the way to building a working prototype at the pilot scale to demonstrate the viability of their concept. Teams have been given the freedom to select their own markets and applications for their technologies with an overarching theme from the Department of Energy to create new American companies and new American jobs in the solar desalination space. Today, these teams are looking to round out their skill sets and build cross-cutting teams capable of taking their innovations from the ideation phase and turning them into reality. As you listen to the presentations today, think about how or if you might be able to contribute to these teams' technologies, or whether someone in your network might also be able to help them further their ideas as well. All the comments we received today from the audience will be shared with the applicable teams so that they may review it before the networking event next week. I would now like to introduce John Leinard, who will be moderating the presentations by the 19 teams today. John H. Leinard V is the Abdul Latif Jamil Professor of Water and Mechanical Engineering at MIT. And during his 3 decades on the MIT faculty, Leinard's research and educational efforts have focused on heat and fluid flow, water purification and desalination, and thermodynamics. Leinard received his bachelor's and master's degrees in thermal engineering from UCLA from the Chemical, Nuclear, and Thermal Engineering Department. He joined MIT immediately after completing his PhD in the Applied Mechanics and Engineering Science Department at UC San Diego. Leinard's research on desalination has included humidification, dehumidification, membrane distillation, forward and reverse osmosis, solar-driven desalination, nanofiltration, electrodialysis, management of high salinity brines, thermodynamic and energy efficiency analysis of desalination cycles. Leinard has directly supervised more than 85 graduate theses and postdoctoral associates and has authored more than 200 peer-reviewed papers. He holds more than 40 US patents and pending applications, many of which have been commercialized in the water industry. He is a fellow of the American Society of Mechanical Engineers, a fellow of the American Association for the Advancement of Science, and a registered professional engineer. With that, I'd like to turn the floor over to John Leinard.
Thank you, Daniel and Shannon, for that very kind introduction, perhaps a little too long for me. I am really pleased to be here today, and I'm really pleased to have the opportunity to hear from all of the presenters. Solar thermal desalination has been an object of study since at least the 19th century, when some of the first large solar stills were developed. And the technology has continued to be advanced in steps over the subsequent period of time. There are some significant constraints that face any solar thermal desalination system. The energy use needs to be very efficient in order to limit the area of solar collectors that are required and the associated capital cost imposed on the system. In addition, because the top temperature of most thermal separations is limited, normally by scale formation, the exergy content of any unit input of heat is relatively low. So the engineering challenges are significant in making these systems effective and energy efficient and cost effective. We also have photovoltaic systems as competitors. All that said, as a thermal engineer, I'm delighted to see the renewed effort around this technology, the efforts to improve the separation efficiency and perhaps to raise the top temperatures as well. Today, we're going to hear about a wide spectrum of approaches to this problem. These will include distillation systems, absorption systems, switchable solvent extraction, sorption technologies, and various other approaches. Some of them based on advanced materials, some of them based on other types of solvents. So without too much further discussion, I'd like to begin the session. What I will do is to introduce each team by name, and I will introduce the captain, and then the teams will tell you about the project for which they are seeking partners. Each team will have 4 minutes to present. We will not have formal Q&A around these presentations, but of course, if you'd like to put questions into the Q&A box, maybe the teams can answer you individually. So with that said, I will move into our first presentation. The first team is titled Heat Storage for 24-Hour Solar Desalination. The team captain is Parker Wells from Acadia, California. Parker, take it away.
Hi, thank you. Well, I'm a ghost, but hi, I'm Parker. I'm the founder and CEO of Element 16. Element 16 is a thermal energy storage technology company with engineers from Brown, Caltech, Virginia Tech, and UCLA. As a company, we've gone through Techstars, SparkLabs Energy, Creative Destruction Lab, and the National Science Foundation I-Core program. We've also received over $6 million in state and federal awards, and this month we were selected for another $2 million DOE Solar Energy Technology Office solar thermal project, which we're very excited about. Could we move to the next slide, please? Our core innovation is using molten sulfur as a heat storage media. Sulfur is a byproduct of the oil and gas industry and is therefore extremely inexpensive and highly abundant. It's about 10% or less than 10% the cost of competing storage materials. Sulfur also has this low freezing point, allowing us to discharge heat at thermal desalination temperatures between 100 and 200 Celsius. Next slide, please. Our thermal energy storage, or TES, uses a single tank design with heat transfer fluid tubes inside a molten sulfur bath. We use liquid storage material in order to benefit from natural convection, allowing for rapid and efficient thermal charging and discharging at constant temperatures and heat rates. Next slide, please. We've built and tested molten sulfur TES units like this one, this demonstration at our facility in Southern California. We've secured funding and initial partners to pilot our technology for waste heat and solar industrial process heat applications. But this would be our first project designed specifically for the specifications and integration requirements of thermal desalination. Our goals, please. Our goal is to use day-only solar thermal resources to feed thermal desalination units 24 hours a day. Next slide. We aim to optimize and design low-cost molten sulfur thermal energy storage technology for the 120 to 200 Celsius range. And we aim to demonstrate and validate operation of our sulfur thermal energy storage for a fresh water capacity of at least 100 cubic meters per day. This will require 2.5 to 4.5 megawatt hours thermal energy storage capacity at around 200 kilowatt thermal discharge rate, while meeting aggressive cost targets to achieve a competitive levelized cost of energy. Next slide. A lot needs to happen to achieve these goals. So we are a solar thermal energy storage team, and so we need a lot of thermal desalination expertise and facilities. We aim to, one, partner with experts to help us design for the requirements of thermal desalination. Two, partner with a host site with the 100 cubic meter per day requirements that can meet that kind of capability. Three, we'd like to work with that partner to identify kind of the site-specific challenges. And four, create a detailed conceptual design with initial process flow, costs, and impacts. Deadlines. Next slide, please. This all must be accomplished by February 9th. We are currently seeking and speaking with project and site partners. We aim to have that certified by the end of this year with detailed engineering in January of 2021. Last slide, please. If you are an engineer, operator, or management of an MED or other thermal desalination facility and are interested in working with us, please contact me. Thank you so much. I believe you're on mute.
That tricky mute function. Thank you, Parker. Our next presentation is from a team titled Solar Thermal Enhanced Evaporation. And the team captain is Professor Natasha Wright from the University of Minnesota. Natasha, floor is yours.
Great, hello, and thank you for joining us today. Our project is a partnership between my research group in the Mechanical Engineering Department at the University of Minnesota and QuadSun Solar Solutions, which is a company based in India with expertise in concentrated solar and evaporation systems. We have received approximately $500,000 US in state and federal funding thus far related to this work. Next slide, please. Options for brine treatment are actually extremely limited for small scale brine producers. So that's those desalination plants in industries that produce less than 100 cubic meters per day. Solutions that do exist are often not cost effective, with standard evaporators and crystallizers having a capital cost of more than $1 million for a 30 cubic meter per day system. In the US, small industrial producers often resort to sending their waste off-site for treatment, which causes an increase in operating costs, both for the original producer as well as for our municipal facilities that are trying to manage that waste. Therefore, there's a need for a modular brine treatment technology that is robust to different chemical compositions and ambient conditions, such that economies of scale can be achieved by installing and selling multiple small units instead of constructing one large plant. And bringing such a modular system to market is our team's goal. Next slide, please. Our innovation is a forced convection enhanced evaporation treatment system that consists of a set of horizontally packed hydrophilic evaporation surfaces. When implemented as part of an HDH or humidification, dehumidification, desalination system, evaporated water can be recovered for use. We use smart control, by which I mean active weather-dependent control of the brine temperature, brine injection rate, and airflow to maximize treatment rate and minimize the levelized cost of water based on the instantaneous ambient conditions. A version of the proposed technology, which is shown in the photo, has been tested both by my research group at the University of Minnesota and by Quad Sun Solar, validating our team's technical theoretical model for the unit's performance. Prototype units are currently being tested at several industrial facilities in India. The brine treatment is increased, brine temperature is increased using concentrated solar collectors as shown on the left. These collectors are designed by Quad Sun Solar in India and have a higher efficiency than standard dishes on the market. This is because the mirrors are factory shaped into true parabolas, in contrast to most other dishes, which are made up of small flat mirrors that approximate a true parabola. Our dish also has a concentration ratio of more than 600, resulting in a smaller receiver with lower losses. To date, approximately 700 of these collectors have been installed in India and 50 in Europe. Next slide, please. Over the next 3 months, we need to validate the market potential for this technology, confirm operation over a wide range of contaminants present in the US industrial brines of interest. To do that, we'll need to obtain water samples from those industries. And we would like to integrate our collector and evaporator into a closed loop HDH desalination system by incorporating a condensing side. As mentioned, we are currently focused and our experiments have currently focused on the evaporation or humidification side. Next slide, please. In order to help our team accomplish this goal as well as succeed in future rounds of the prize, we do need assistance in a few areas. The first is that we're looking for potential test sites for small volume brine management and water recovery from industrial waste or remote desalination. It's even better if you have a potential use for selectively precipitated salts of low purity. So for example, 95% sodium chloride or 95% calcium carbonate. If you can't be a test site for the prize, but you are still a small volume producer, we'd still love to hear from you as we try to understand the market. We'd additionally need folks that specialize in pump and heat exchanger selection for highly saline brine flows. Anyone with an innovative solution on the condensing side, we are open to changing our current design since that it hasn't been our focus. And any existing companies that are open to a joint venture or partnership with Quad Sun Solar to allow for US-based manufacturing. Thank you.
Thank you, Natasha. Our next presentation is from a team titled No Air, Super Vacuum Gap Nanomembrane Distillation. The team captain is Professor David Warsinger from Purdue University with a team based in Gainesville. David, take it away.
Thank you, John. So our approach uses membrane distillation and it can achieve a super vacuum via hybridization with thermal vapor compression and novel membrane nanomaterials. Next slide. Our team consists of Purdue and 2 industry partners, NICAB Desal and Focus Sun. We also have a connector, Nashwell, and an intended supplier, Aquasteel. Next slide. To understand our performance, we can look at the gained output ratio versus the second law efficiency, and we see that these metrics are a very strong function of temperature. We can map out the various other competing technologies onto this contour plot, and we can see that multi-effect distillation with TVC can access higher temperatures and thus superior performance. Notably, the most efficient membrane distillation system demonstrated so far has been by our industry supplier, aqua still. We intend to achieve higher efficiencies than this by accessing higher temperatures via hybridization with thermal vapor compression. To do so, we avoid the diffusive regime that normally occurs in an air gap membrane distillation process by achieving a very, very high vacuum. Now, notably, if we graph the velocity of water vapor flowing in these confined spaces, we see very slow velocities in traditional membrane distillation. However, similar systems with different geometries, such as heat pipes, can achieve dramatically higher flow velocities, even reaching the sonic limit 4 to 5 orders of magnitude higher than you typically achieve in membrane distillation. And so thus we intend to achieve much higher flux as well as energy efficiency than conventional thermal desalination systems. Next slide. Our system has 3 core components. It begins with a CSP system that uses a Fresnel mirror to concentrate to higher temperatures than conventional thermal desalination above 160 Celsius, combined with thermal storage. This high temperature, high pressure source goes to a thermal vapor compression system, which uses an ejector as well as spray evaporation to achieve additional water recovery and increase the overall efficiency. This ejector pulls the vacuum on the TVC components as well as the membrane distillation system, thus allowing for a higher vacuum. We have a novel material combination to achieve higher performance, which we'll see by comparing to conventional systems. So a conventional air gap membrane distillation system has air, as you see in green here, and water vapor that slowly diffuses through the air onto the condenser surface. However, if we add a novel material as a membrane layer and pull its very tight vacuum with the ejector, we can achieve a different flow regime where we have pressure-driven flows and dramatic velocities that occur in the system. And these type of materials have not been applied to desalination, but are used in membrane dehumidification. And they reject all air, N2 and O2, but not water vapor. Next slide. Our process has fairly reasonable costs, and we believe some decent advantages compared to competitors. And these are enabled by the high vacuum. And we think the energy efficiency, small scale operation, and solar integration are all excellent. And it has lower complexity than the other highly efficient multi-stage thermal desalination systems that are applied widely today. And with TVC and MD, as well as some anti-fouling benefits, we can achieve very high salinity water treatment. Next slide. In terms of our teaming needs, we have a testing site planned out, and so we're looking for more regional funding partners that are nearby the High Plains Water District in the Texas area. And in particular, we're looking for manufacturing partners for future scale up, especially for thermal vapor compression. We'd also like some more vendors for the pre-treatment and site testing components and business potential partners for implementing this for oil and gas and other high salinity applications. Thank you.
Thank you, David. Our next team is TSSE Desalination of Hypersaline Brines. The team captain is John Sass, based, I believe, in Santa Barbara, California, in collaboration with Columbia University. John, take it away.
Thank you very much, John. As John just said, my name is John Sass. I'm the team captain for technology called TSSE, Temperature Swing Solvent Extraction, based out of Columbia University. We have engineering support from Bechtel, financial support from numerous partners that represent on this slide from Social Impact Capital, and commercialization is being overseen by Trident Desalination. I should have also probably included Sandia National Labs on this slide, but as a recovering lawyer, I did not ask them for permission to use their logo. Next slide, please. So our project is based around temperature swing solvent extraction, which is a non-membrane thermally driven desalination technology. The key takeaway here is that while the technology is thermally driven, the system does not rely upon evaporation distillation. Instead, it is a solvent extraction based technology that uses low polarity solvents and extremely minor temperature swings, often less than 80 degrees Celsius. The system is therefore optimized to treat high TDS brines in this 55,000 to 300,000 range. The low temperature requirements to this and low energy systems provides a major advantage over thermal crystallizers and brine crystallizers. Our proposed pilot is going to demonstrate this technology on the concentrates from a brackish water reverse osmosis facility or on a similarly clean TDS brine stream. Next slide, please. So what are our ultimate goals for this project? First, we want to construct a continuous use desalination system that's actually capable of achieving zero liquid discharge for a water sample up to above 55,000 TDS. We want to test a modular pilot system with an integrated solar thermal energy system capable of producing in excess of 100 meters a day of fresh water. And we want to monitor some select key metrics as this project develops out. In particular, our solvent recovery regeneration rate. Our solvents in this process are catalytic, but they are not consumed. This allows us to effectively lower our ongoing operational cost expenditures and makes us extremely cost competitive. Next slide. So our key action items. We need to identify a suitable host site as well as a domestic solvent manufacturer, partner with a solar thermal provider and incorporate that into our current system process design. Finalize some of these key ratios based upon the type of solar thermal system we're going to be utilizing, as well as identifying any local location needs, and then obtain all the necessary permitting for this pilot. Next slide. And this is where we're at. We've currently engaged with in multiple discussions with individuals, and we anticipate having all this information by the end of the year. We do believe that we'll be able to finalize our host site locations again by the end of December 2020. We will be then incorporating the solar thermal system into our process design by the end of January and having everything ready to go by our February 9 deadline. Next slide. So what we need, we are functionally a desalination company. So mentorship and assistance in the solar thermal space would be very much appreciated. We have looked at various different types of solar thermal energy, solar furnaces, but we would love to hear from the industry about best practices. We again are looking for different host sites, and if you do have either an inland concentrate or a high TDS brine stream of 55,000, that's fairly clean, we'd love to hear from you. And then finally, we would love to talk to domestic manufacturing groups so we can produce everything here in the United States. Next slide. So that's me on the left. I oversee the commercialization aspect of this. Professor Yip at Columbia is on the right. I would ask that you contact me since it's a rather busy time for anyone in the academic world with finals coming up. And thank you very much. I'm looking forward to hearing from you.
Thank you, John. Our next team is titled Sorption-Based ZLD Technology. The team captain is Sajjad Bingham, and the team is composed of researchers from Oak Ridge, Michigan Technological University, and Arctic Solar. Sajjad, please go ahead.
Thank you, John. Good morning, everybody. Thank you for taking the time and attending the meeting. As John mentioned, my name is Sajjad Bingham, and I'm an assistant professor at Michigan Tech. So our project aims at development of sorption-based ZLD technology. So the core concept is to use a salt to desalt a salty water. This is a collaborative project between academia, a national lab, and industry. So here in this slide, we see our team composed of Michigan Tech, Oak Ridge National Laboratory, and Arctic Solar Company. Next slide, please. So current desalination systems have three major limitations: intensive use of high-grade energy for ZLD treatment, zero liquid discharge treatment, chemical scaling that happens at high temperatures, and concentrated brines, which harms the environment. Next slide, please. So our proposed project addresses this shortcoming by novel sorption-based ZLD concepts. So what we do, we use sorbent to achieve ZLD operation. So here we use a strong hygroscopic properties of a salt that is able to capture large volume of water vapor from a brine slurry. In addition to that, we are able to operate our system, our desalination system at high temperature through high temperature desorption process, which enables us to leverage large exergy that is available at high temperatures through existing solar collectors and thus realize high thermal efficiency. Next slide, please. So here we can see a layout of our system. As we can see here, our goal, our target is to have a modular desalination system for a small scale mobile application. Next slide, please. So we have conducted extensive thermodynamic modeling to see the technical feasibility of our systems. So left figure shows an example of energy flow calculations that we have done with a system that is using 6 MEDFX and the sorption unit. As we can see in the right figure, our system has a total energy consumption of less than 70 kilowatt per cubic meter of distilled water at 100% ZLE operation. Next slide, please. So here we see our action items for the project. We have divided our action items into 2 categories of design and testing. In the design category, we need to do cycle analysis, component analysis, and system design for the targeted applications. And in the testing category, we need to fabricate and test individual components and perform testing of the entire systems. Next slide, please. So here we see our deadlines for the projects. So our deadline for the teaming stage is like other teams, February 2021. But for the sub-scale design and testing is a spring 2022. And for the full scale design and testing is spring 2024. Next slide, please. So we are looking forward to collaborate with experts in design of compact high salinity crystallizers, as well as a field testing site for our projects. If you see an interest and you want to learn more about our project, please contact us and we would be happy to share more information with you. Thank you for your time and attention to our project.
Thank you, Sajjad. Our next team is portable treatment of oil and gas wastewater with ZLD. The team captain is Bahman Abbasi, and the team includes researchers from Oregon State, Michigan State, and the University of Nevada. Please go ahead, Bahman.
Thank you, Professor Leinart, and thank you, ladies and gentlemen, for the opportunity to present here today. My name is Bahman Abbasi, and along with my partners at Oregon State, Michigan State, University of Nevada, and Rogue Approach, next slide, please. We are working to develop a low-grade solar thermal-driven process for a containerized, portable, modular, and scalable oil and gas wastewater treatment. This figure is our vision for an ultimate commercial unit where you have these containerized unit that you can drive from different wastewater pools and treat them on site. Our process relies on spray evaporation and selective condensation, and we have filed 3 patents based on our inventions. All the components and processes have been demonstrated in our laboratory. And next slide, please. So the goals of the project are to treat oil and gas produced water with more than 30% contaminants, including suspended solids, dissolved solids, heavy organics, and VOCs, while maintaining the cost below $3.50 per meter cube and reach better than 98%, even 99% in a once-through process. Ultimately, our pilot unit, we would like to achieve production rate of 100 meter cube per day. This is a picture of one of our many experimental setups from which we were able to purify water to better than 97.5% purity. We believe we can improve that even further. Next slide, please. So our action items are to finalize and present our designs for the commercial unit to NREL and DOE, complete our negotiations about the fabrication and operating the pilot plants, which we aim to build, and finalize the test site with all the related protocols and requirements, which are pretty stringent for the type of oil and gas wastewater we would work with. Also, we're going to negotiate with potential commercial partners because our ultimate goal is to push this out to the market and see it on-site treating water, one of our most important tasks. Next slide, please. We have a detailed internal timeline for all these tasks based on how far along we are. We have divided these, and we believe that between now and February 9th, we will be able to accomplish all of what I described to you, well, except for building the plant, which will take 4 years. Next slide, please. So the expertise request is, even though we are in negotiations, if you're interested in our work and if you're skilled at building pilot plants, packaging, operating procedures, we would love to hear from you. If you operate a test site and have available space, sun, and disposal procedures and permitting requirements to deal with oil and gas wastewater, we would also love to hear from you and speak with you. And of course, you're looking for commercial partners. If you're active in the oil and gas produced water space, we want to use the real oil and gas produced water in our pilot plant. We need some real world know-how about the current technologies and market network so we can push this out as efficiently as possible. And next slide, please. If you have any thoughts, comments, you would like to discuss our technologies or share your vision with us, please contact me, Bauman Abbasi, or our lead engineer at Roke Approach, Mr. Tyler Hudson. Thank you very much for your time, ladies and gentlemen.
Thank you, Bauman. Our next project is titled Forward Osmosis, Biomimicry at Work. The team captain is John Webley at Trevi Systems in Roanoke Park, California. John, please take it away.
Good morning, John. Good morning, Shannon. So our team is named Hawaii 5-0 for Forward Osmosis. It's a partnership between the National Energy Laboratory of Hawaii, Trevi, and Sandia or PNNL as a resident expert for us. Next slide, please. So the existing plant funded by the Department of Energy under a SEDO grant is for a 500 cubic meter per day system. So we're now stepping up to the next size in production to move away from sort of prototyping to full-scale pilot. It's designed to be at an equivalent price to an RO system in terms of capital cost. Therminology, 37 kilowatt hours a cubic meter, operating at 85 degrees. The draw solution is removed with a hot nanofiltration system, which saves energy, so you don't have to cool it back down and then reheat that retentate. We would like to see at least 50% and targeting 60% recovery on the plant. We have an offtake agreement with an on-site algae farmer you'll see there in the picture. And there's an on-site low temperature CSP array, although the storage hasn't been well developed. So that's definitely an opportunity for somebody to partner with us there. Now, when you build these large scale plants, you're always looking to minimize, as John had mentioned, thermal energy. And so we've been looking at these draw solutions that we use. And one of them is the one we currently use has a very large exothermic component, a heat of mixing, which is lost into the brine. Looking at draw solutions, we've come across some endothermic draw solutions that draw heat from the environment, which makes it much easier to phase separate. We also have found a few that switch on CO2. And so we think there could be blends of these different compounds that will give us a lot of benefit. Next slide, please. So recognizing the capital cost of the CSP plant is about 4 times the cost of the water plant that it powers. If you remember that ratio, then any dollar I save on the FO plant in terms of energy gets multiplied by 4 in the capital cost of the solar plant. So our target here is to start at a fairly conservative goal of going from 37 to 30 kilowatt hours, although I'd like to see lower than that. We will be deploying in this next phase in multi-megawatt polymeric heat exchangers. The benefit of these forward osmosis systems is there's no phase change between latent and sensible heat. Everything remains in the sensible domain. So all our heat recovery is sensible. So the cost of the heat exchanger sets a big part of the cost of the system. And of course, forward osmosis membranes haven't been standing still, and we'd like to really keep pushing them so we can push recoveries beyond 65%. Next slide, please. So what we'd like to do is review all the existing CO2 switching polymers out there. And I think PNNL has been very busy in that area with their carbon capture and sequestering development. And that's where these two different approaches kind of parallel each other. We need it for a draw solution. They would like to sequester CO2. So there's benefits to both. We would like to, of course, work on a timeline with our folks in Hawaii to when we could do these upgrades. And although we've been developing these polymers for 3 years, we definitely need support from national labs on computational screening because the task in front of us is quite large to screen thousands of components. Next slide, please. And so One of the questions I have is, who would be a good partner that has these kind of in-house computational capabilities to help us screen hundreds, if not thousands, of these new components that they've been developing for CO2 sequestering? And of course, we're very interested in working with a solar thermal storage partnership. Right now, we use hot water. And of course, we have to really see how far we can push forward osmosis to see if we can come up against RO in terms of thermodynamic efficiency. Next slide, please. And that's my contact information. Please feel free to reach out to me. Thank you very much.
Thank you, John. Our next team is STREED, Resonant Energy Exchange Desalination. This is a team from Rice University, captained by Pratiksha Dongare. Pratiksha, please go ahead.
Yeah, thank you, John. Hello, everyone. My name is Pratiksha Dongare, and I'm representing Team STREED today. Our team consists of researchers like Alessandro Alavastri, Oran Newman, and myself, who have been working on developing innovative nanophotonics-driven desalination systems for more than 5 years under guidance of Professor Hellas and Professor Nordlander at Rice University. And our business development will be led by Andrew Trillivon, who has extensive sales and business development experience in oil and gas industry. In initial stages, we will test our prototype at Bureau of Reclamation's facility at Alamogordo, New Mexico, where we have already worked in the past. Next slide, please. So as you can see here, our goal is to produce clean water from oil and gas wastewater using just solar thermal energy. Currently, 40% of the produced water from oil and gas is just disposed of in injection wells, and this bears huge costs and environmental impacts. So our solution is STREED, which stands for Solar Thermal Resonant Energy Exchange Desalination. So STREED combines two key components developed at Rice University. The first is the resonant energy exchange, which allows solar energy to be accumulated and recycled within our modules. And the second is nanophotonics-based desalination, which allows efficient light to heat conversion for vaporization and water purification. And STREED is a membrane-free robust system which provides operation even at night time. Next slide, please. So as you can see here, this graph shows theoretical predictions of 24-hour STREED module operation. And here, the energy accumulated within each module during the day can be reused to guarantee operation even after sunset till next sunrise. According to our models, 1 meter square STREED unit can produce 20 to 30 liters of water per day, and arrays of STREED units can be combined together to reach any target water capacity. Next slide, please. Next slide, please. So our project will progress through achievement of stepwise goals on the way. We want to first demonstrate a 1 meter square proof of concept unit at Rice, followed by a modular unit capable of treating 1 meter cube of water per day. And then we will combine multiple units together to reach 10 meter cube per day. And these testings will be done at Beggendorf in New Mexico. And after that, in the final stage, we want to extend this to reach a treatment capacity of 100 meter cube per day at an actual oil and gas field test site, which will be decided in our teaming phase. We will keep working on business plan development and commercialization strategies throughout the execution of these goals. Next slide, please. So in line with our goals, our action items will first focus on STREED system development through research and fabrication of optimized units. We'll then move to testing and scaling up through extensive engineering. And in parallel, we'll keep working on business plan development through market research and customer discovery to identify our next commercialization steps. Next slide, please. Our timelines for goals and action items can be seen here. And our key milestones are reaching technology and market validation with successful proof of concept design by 2022 and developing a ready to deploy 100 meter cube per day treatment capacity commercializable system by 2024. Next slide, please. For the success of STREED development, we are looking for a senior engineer who has experience in design and engineering of water purification systems to strengthen our engineering capabilities. And we are also looking for vendors to provide specific system components and machining services to help us for bulk machining of parts and designs. Next slide, please. So if you're interested in knowing more, please feel free to contact Alessandro or myself at these email addresses. Thank you so much.
Thank you, Pratiksha. We'll now move on to another team. This one is titled Zero Discharge Multi-Effect Absorption Distiller. It is from a group called Green Blue, based in Princeton, New Jersey, and the team captain is Howard Yue. Howard, please go ahead.
Thank you, John. So I have 4 minutes today to tell you a little about Green Blue. We're based in Princeton, New Jersey, and we founded the company with a core belief that eliminating brine discharge and sustainably distracting dissolved solids is desalination's future. Our solution will be a zero carbon, zero discharge, zero infrastructure, brine disposal, desalination, and brine mining. Next slide, please. Looks like they didn't get my new slides. So I'm going to tell you a little about the project. We'll be the first to use multiple effect adsorption for desalination. This is a technique that's different from the other techniques in that it is not a hybrid approach. It is a pure adsorption approach. We've received 3 patents to date for this, and we're currently under a DOE award to develop a prototype of the system. It'll be the first design to use a containerized low CapEx, low OpEx ZLD module. Our new crystallizer will be the first to produce separated salts using a pure physical process of evaporation requiring no chemicals. Will be the first ZLD process to be zero carbon using solar heat. And we hope to be the first to disrupt the desalination market by selling not just the water, but also brine disposal and separated salts. Next slide, please. So our goals for the project are to demonstrate innovative new fractional crystallization evaporator condenser, to demonstrate our high efficiency multiple effect adsorption cycle. Here I show you a picture of our latest small single effect prototype, which is operational and separates saturated brine into solids and distilled water under 1 ppm. We plan to manufacture Green Blue's 60 cube per day containerized product and prove that the high profitability of zero waste desalination. Next slide, please. Our action items include completing the manufacturing plans for the adsorbent and adsorption beds, the evaporator condenser, our sensor packages, valves, actuators, and pumps. We have developed manufacturing techniques and methods, and we have to test and debug those. Next slide, please. Our current CETO award from DOE is due for completion in 2022. That includes a 10% scale prototype of our multiple effect adsorption cycle. It includes a demonstration of the efficacy of this cycle. Our full scale 60 cube per day containerized product demo is expected in 2023. 2 of these will be used to fulfill the desalination prize here. It'll be ZLD capable and produce pure separated salts as a product. Next slide, please. We have some needs in the simulation of flow distributions in complex geometry, including 2-phase flow, vapor flow, and entrained salt crystal growth, flow, and distribution. We have a number of proprietary technology needs, which we'd be happy to discuss with you in a private setting. Next slide, please. I know 4 minutes is a very short time to describe what we're trying to do. Please visit our website at greenblue with a dot between the B and the L, and you can contact me at the address shown. Thank you.
Thank you, Howard. Our next team is modular, inexpensive solar thermal evaporative-based desalination. The team captain is Sean Torres, and they are from PSI in Andover, Massachusetts. Sean, please go ahead.
All right, thank you. Actually, our team name is Potent Solar Potables in honor of Alex Trebek. And That's because there's nothing more potent than the notion of supplying clean drinking water from desalination using renewable solar energy. So our team at PSI is a R&D company. We really focus entirely on research and development of various technologies, including several water purification and desalination technologies, as well as other pilot plants within the Department of Energy's tech development portfolio. Our team that you see on the screen here, this is most of the people who are involved in the program. We have mechanical engineers, we have opticians, and we have chemical engineers on the team. So we're coming at it from all those angles, and we are looking to both design and then manufacture, at least through the pilot phase of the program. Next slide, please. So the MISTED system, as described by Professor Leinhard, is a multi-stage flash system. The goal of this development is to make multi-stage flash as simple and as cheap in the apparatus as is possible. And that's, of course, every system wants to be cheap, but this approach is in contrast to trying to produce a lot of water by making the system ultra efficient, which past research has shown ends up being very expensive because you need to have a very precise apparatus. Next slide, please. So, of course, our goal in the teaming phase is to build a really great team. We are seeking to advance the maturity level of our prototype. For the purposes of this phase, we not only modeled, but also built the first stage of a solar MSF system. We are going to do some additional modeling in this current phase, as well as build another prototype. And then we are also seeking, as you'll see in the next couple of slides, we're seeking some partners, even though we're partway through the process of formalizing our relationships with some of our partners already. Next slide, please. So we are seeking a host site. Our innovation can use both seawater and brackish water, can use various different sources. Our goal is to make drinkable water specifically, rather than only focusing on remediation. We're also looking for a company that may operate a site, and that could be a water district or a remediation company. For permanent installations, we're seeking a construction firm. We are also seeking manufacturing that's based in the US for a few of the components of the device, although PSI will likely manufacture some components in-house, and then finally a test facility that would likely be a DOE facility. Next slide, please. Our timeline is shown on the screen. So we're anticipating having formalized agreements in the month of January, and then finalizing everything by the beginning of February in anticipation of the 13th deadline. Next slide, please. So again, the expertise ask is PSI is the innovator here, and we're going to be doing the modeling and building the early stage versions of the plant. And then our manufacturing partner and our operations partner would come in at that time, while the national lab test facilities will come in the very next stage of the program. Next slide, please. And finally, you may contact me directly if you're interested in being part of our team. Thank you.
Thanks very much, Sean. Our next team is Solar Aquaflex Off-Grid Solar Still. This team is from Vanderbilt University, and the team captain is Drew Horseman. Drew, the floor is yours.
Thank you, Dr. Leinhard. So yeah, my name is Drew Horseman, and I'm the leader of a group of researchers from Vanderbilt University. And next slide, please. So our product basically is a solar distillation device. So we've designed our product so that it is completely flexible for enhanced portability. It's completely passive, meaning it requires no external energy sources other than the heat from the sun or any external mechanical moving parts. And finally, We've designed our system to be multiple stages so that it utilizes the heat from the sun more efficiently and results in higher freshwater productivity compared to conventional solar distillation devices. Next slide, please. So right now we have two main groups that we can categorize our customer segments into. Next slide, please. One are those that are looking for drinking water in off-grid scenarios. So that includes humanitarian, disaster relief, recreational, and small-scale military operations. Here we can produce 5 to 10 times the amount of fresh water as compared to a similar sized one-stage distillation device. And also our device is so portable that one person can carry it and basically carry enough device area to provide drinking water for 40 to 80 people. Next slide, please. So the second category is basically end users with evaporation ponds. So whether that be an industrial facility with evaporation pond at the end of their water treatment process, or a salt production operation where they're using evaporation ponds to concentrate their salts. We effectively increase the evaporation rate by a factor of 60 compared to just normal ambient evaporation. And that either allows these industrial facilities to decrease their evaporation pond area and make it easier in obtaining permits, or for these salt production operations, that increased evaporation rate increases their production of salt crystals and the overall product turnover. Next slide, please. So our goals for this stage of the project are to basically show that there is a pathway to commercialization and that someone is actually interested in using our product. So what that entails is conducting customer discovery interviews to basically identify the key customer segment that we should focus on right now and that has the biggest problem we can add value to. Then we'll move forward in optimizing our prototype so that we address those problems that we identify with that key customer segment. Next slide, please. We plan to solidify our business model, and that entails identifying key partners for manufacturing and also estimating a competitive product pricing strategy based on what we've identified in the key customer segments' needs and wants. And finally, we hope to identify a prototype testing location, and the deadline for these goals is January 8th. Next slide, please. So we're asking for any help for any experts out there in attendance. If you have any connections or experience in these customer segments, whether it be potential testing sites or if you can help in customer discovery, we greatly appreciate it. If you have any critique on our business model, we'd also be glad to hear your advice. And finally, if you have any connections with manufacturers or possible material suppliers and membranes or layered materials fabrication, please feel free to contact us at these emails below, and thank you for your time.
Thank you, Drew. Our next team is working on brine concentration with managed salt precipitates. The team captain is Andrew Lowenstein, and they are led by ALI Research in Hopewell, New Jersey. Andrew, please go ahead.
Thank you, John. I'll start by thanking IDA and NREL for this opportunity to connect with potential team members. Our team is named Brine Zero, a name that captures our goal to provide an affordable, environmentally responsible means of brine disposal. Brine Zero's principal team members are Dr. Todd Rossi, Mr. Clark Easter, and myself, Andrew Lowenstein. Todd and I are Brine Zero's two current senior officers. Clark's role is best described on the next slide. Next slide, please. Brine Zero's entry into the market will be through Clark's efforts to expand water resources for farmers in California's Central Valley. Using state-of-the-art reverse osmosis, or EDR, Clark, as a project developer, can specify desalination facilities that upgrade brackish water to irrigation quality at 40 cents per cubic meter, but only if the cost of brine disposal is ignored. Clark needs a technology that reduces today's cost for inland brine disposal by a factor of at least 3 if he is to deliver water to farmers at a competitive 60 cents per cubic meter. Brine Zero system, shown here as a second stage to an RO or an EDR facility, will provide the required threefold cost reduction. Next slide. Brine Zero's core technology is an exceptionally efficient thermal distillation process that we've named diffusion gap distillation, or DGD. Although I don't have time to explain the operation in detail of DGD, those familiar with air gap membrane distillation will see strong similarities between the two technologies. In fact, DGD is in effect membrane distillation without the membrane. There is a YouTube link that appears on this slide, and I will post it on the Zoom chat for those looking to see a more detailed explanation for the operation of our system. Important characteristics of DGD are: one, its high thermal efficiency, gain output ratios can be over 10. Two, its low first cost, which follows from implementation with plastic heat exchangers. Three, its very low electrical demand. And four, its scalability, which makes it a practical solution for small farmers. Let me next highlight several of our goals. Next slide. We are now working to improve operation with brines saturated with sparingly soluble salts in laboratory models that, as shown in the picture in this slide, have full-sized 8-foot-long plates. Once we move the technology into the field, we will want to demonstrate performance that is consistent with brine disposal at $3.40 per cubic meter or lower, which is the price point Clark needs to begin selling systems to inland farmers. A longer-term goal will be to expand Brine Zero into other applications. Next slide. Of course, our most pressing action item is to submit a strong teaming proposal before the February 9th deadline. A number of tasks must be completed before the proposal is submitted. The one most relevant to today's pitch is the first one shown on this slide, to fill several gaps in our team's collective expertise by adding critical members. Next slide. In this slide, I'm going to only speak about the deadline most relevant to my presentation, and that would be the third one, where we want to complete our team by December 18th so that new team members can help us meet the February 9th deadline for proposal submission. Next slide. The DGD process has advanced from a concept through proof of concept validation to a nearly commercially ready status in work conducted at AIL Research. As its name implies, AILR is organized for research. And although it will support Brine Zero as a team member, it cannot alone provide all the engineering support needed to design, build, install, and operate the DGD facilities needed by Clark Easter. In particular, as explained on this slide, Brine Zero needs an individual or company with expertise designing, deploying, and operating water treatment systems, and more specifically, automated systems for continuous handling of precipitating salts. Next slide. With that, I'll conclude my talk, and thank you all for attending.
Thank you, Andrew. Our next team is working on urban solar desal building, an urban solar desal building. The team is captained by Yunho Huang from the University of Maryland. Yunho, please go ahead.
Yeah, hello, good morning. Yeah, thanks for introduction. Yeah, we are from Urban Solar Desalination Building. We are from Center for Environmental Energy Engineering of the University of Maryland. Yeah, I'm a team captain and I'm working with the 4 members, Hyung-sung Kim, Yamil Bauer, Tao Kao, Nicole Kicker. Yes, next slide, please. Yeah, we are forming a team now. We are leading the project supported by our university for legal aspects and government funding securing. And potential partners are listed there. We are working with the Arctic Solar about the solar thermal collector design and manufacturing of those. And we are talking with the WBCM for engineering aspects. we are contacting Ocean City Public Works for potential testing site. And we are also contacting membrane manufacturers for modular design as well as the manufacturing of the membrane itself. The next slide. Here it shows our concept design. Basically, our idea is using multi-stage vacuum membrane distillations heated by the solar thermal collectors that is combined with the solar thermal storage tank and also the PCM materials. And then this system is combined with a barometric water column so that we can eliminate energy consuming pump. So therefore system can be more energy efficient. And our internal design is vertical type. So therefore, this system could be compact and require only small land spaces. And we can supply the water as a decentralized system so that we can minimize the heat loss and gas storages. Next slide, please. So at this time, we are trying to complete our teaming so that we are defining our teaming partners for manufacturing, engineering, and as an end user. And also we are defining detailed tasks for each member and making a regular agreement for the competition. And then we'll be submitting second stage proposal. Next slide, please. In the next round, we'll be completing our detailed design. Then we'll be selecting test site, designing vacuum membrane distillation module, designing thermal solar collectors, bench scale testing of the membrane collectors, and the final design for the solar desalination system, which has the target capacity of 100 cubic meter per day. And we will be preparing, purchasing, and the component and systems, and then plan for installations. Yeah, next slide, please. Then the final stage, we'll be developing prototype, then testing of it, and data analysis. So that we can, for this matter, we will be purchasing all the materials and insurances and manufacturing membrane module and solar thermal collectors, installing all the component and providing operation and safety manuals to the operators, then testing and performance analysis, whether we can achieve our target or listed there. Yeah, next slide, please. Regarding the technical goals, basically we are developing low-cost thermal solar collectors filled with PCM materials so that we can provide 24 hours of the operations, and we'll be optimizing entire system and designing vacuum membrane distillation modules so that we can achieve target metrics in terms of levelized cost of the water and levelized cost of the heat. And we'll be reusing the wastewater using forward osmosis membrane to reduce the environmental impact by discharge. Next slide, please. Here is list our action item until February to submit our second stage proposal. As I mentioned before, we'll be finalizing our team members as of today, and then we'll be finalizing each task for each team members and defining task load by next week, and writing a regular agreement and preparing the signature of that, and then starting a proposal writing by end of this year. And we'll be completing our proposal for second stages. Next slide, please. Right now, we are looking for more team members, especially we are looking for commercial partners for membrane. Although we have some potential list of the candidate that we are contacting now, we are looking for more membrane manufacturers and partners. Next slide, please. So here's my contact information. I have telephone number and email there. So please contact me for any questions, or if you have any interest to joining our team, then that would be great. Yeah, thanks for your attention. Thank you.
Thank you, Yunho. Our next team is working on membrane distillation with ceramic membranes. The team captain is Professor Jeff McCutcheon from the University of Connecticut. Jeff, please go ahead.
Thanks, John. Great to be here today. Thank you for the opportunity to present. I'm from the University of Connecticut and the Connecticut Center for Applied Separations Technology, and we're developing a ceramic membrane platform for membrane distillation. Next slide, please. Our team consists of a group of manufacturers as well as national labs that can help participate in a number of the different aspects of this project. This actually came out of an existing award from the Solar Energy Technology Office, where we developed a membrane in collaboration with Fraunhofer in Germany. And now we're planning to integrate that in with a solar collection system with the help of Arctic Solar, as well as some expertise at NREL and Oak Ridge National Laboratories. And so we're excited for this very diverse team with a lot of different backgrounds in technical expertise. Next slide, please. So I mentioned that this was out of an existing CEDO award, which was part of the Sunshot Initiative to identify new technologies around solar-based desalination technologies. And we've identified that ceramic membranes for membrane distillation, in particular vacuum membrane distillation, offer unique advantages over existing polymeric membrane platforms. While polymeric membranes have largely been used in MD in the last 20 or 30 years, ceramic membranes offer more chemical and thermal robustness and enable the use of MD at much higher temperatures. And given that many solar systems can operate at higher temperatures than those that can be withstood by polymeric membranes, maybe 60 or 70 C, we believe we can get better performance, smaller membrane areas, and other advantages in system design by using higher temperatures for MD. And so we will use this prize as a way to demonstrate the use of these membranes in an actual system. Next slide, please. So our goals are to integrate these ceramic membranes into a VMD pilot and to demonstrate that as part of a ZLD process with brines. Our target is, of course, brines here because that's where most evaporative technologies find foothold when they're looking at comparison to other technologies in desalination. We have some demonstration options on our campus for maybe an early stage shakedown at our power plant, which has an integrated wastewater reuse facility, as well as our seawater intake facility on Long Island Sound. But ultimately, we will look for a brine producer, such as a oil and gas producer, or inland brackish water producer that needs a ZLD type system to demonstrate in the third phase of this prize. Next slide, please. So the action items we have for this phase of the prize before our February deadline for the next phase is to finalize some basic designs or use of the ceramic membranes in an integrated system with our partners. We want to also integrate with our connections to the National Alliance for Water Innovation, the DOE's $100 million water hub, to do some more quantifiable TEA analysis around the technology, a techno-economic assessment to really identify the value propositions of this type of system, and then to find our demonstration partner, which will help us in the later stages of this prize. Next slide, please. And that's really where we're asking for some expertise and some partnering. If you're a ZLD operator or work with complex wastewaters or mining wastewaters, please do contact us. We would love to talk to you about possibly partnering with you for a demonstration of this technology. Next slide, please. And so we hope to have our team fully formed by the end of December and then prepare the next phase of our proposal by February. Next slide, please. So thank you very much for giving me the opportunity to speak to all of you today. You can please contact me at this email, or you can also contact our Director of Business Development, Dr. Sean Young, who's helping with our teaming exercises as part of this prize. So thank you very much.
Thank you, Jeff. Our next presentation is about mimicking the rain cycle using traveling liquid beads. The team captain is Professor Sung-Tak Ju at my alma mater, UCLA. Sung-Tak, please go ahead.
Thanks, John. Hello, we are a team based at UCLA. So in addition to myself, I have two colleagues, Professor Eric Hoke and David Jaspi, and our students and other colleagues, and we're also looking for partners outside UCLA. At UCLA, we're developing a special kind of hidden mass exchangers based on traveling liquid beads, and we want to employ them for energy efficient thermal desalination, especially for hypersaline input water, such as brine discharge from our plants, produce water from oil and gas fields. We'll incorporate these exchangers in a so-called humidification and dehumidification process, or HDH process, powered by solar thermal energy. As you all know, HDH process mimics the natural rain cycle. Click, please. Solar thermal energy will be used to heat feed water. Next, please. Which is allowed to evaporate in a humidifier. Next, please. Water is then carried by air to a dehumidifier. Click, please. Where it is condensed to form pure liquid water. Next slide. One big technical challenge for HDH system, as mentioned multiple times this morning, is the need to improve its thermal efficiency, which directly translates into lower operating costs and hence lower levelized cost of water. The major practical limit on thermal efficiency is posed by heat and mass exchangers that form the humidifier and dehumidifier. Next, please. To this end, we develop a new kind of direct contact heat exchangers and mass exchangers based on liquid beads traveling down an array of inexpensive polymer strings. Next, please. When liquid flows down a vertical string, click please, the interplay between surface tension, gravity, and other forces leads to very interesting flow instability. Click please. This instability generates a series of traveling liquid beads. Note that the flow is purely driven by gravity, and we do not need pressurized liquid, just like in spray columns. Click please. We'll see some videos of the liquid beads traveling down. Next, please. These traveling liquid beads act as radial sinks for water vapor, greatly enhancing mass transfer. Internal circulating flow within each bead also enhances heat transfer across the liquid layer. We form these liquid beads over an array of polymer strings to build a humidifier and a dehumidifier, as demonstrated schematically here. By providing straight, contiguous path for airflows, our exchangers also substantially reduce pressure drop in the gas stream and thereby reduce fan power requirements. Next, please. Over the past few years, we have performed a systematic study to establish scientific understanding of the flow instability and heat mass transfer phenomena. We also built a prototype humidifier and dehumidifier using our multi-string heat and mass exchanger technology. Our dehumidifier is compact, lightweight, and inexpensive, and offer more than 3 times the heat and mass transfer performance than existing devices. We are now translating our learnings from these basic studies to demonstrate an integrated HDH system in a pilot study. Next, please. We are looking for some experts in different areas. One is commercial entities interested in either investing in or licensing our technologies. We're also looking for engineering construction firms who will actually build the test pilot sites and also the pilot test sites that we can utilize to demonstrate our system. Next slide. If you're interested in exploring partnership with us, here's a contact address. We have a special email address that's specifically dedicated for this purpose. And we look forward to hearing your comments and feedback. Thank you.
Thank you, Sung-taek. Our next presentation is about switchable solvent water extraction from brine. This is a team captained by John Webley, again, from Trevi Systems, in collaboration with Aaron Wilson at Idaho National Labs. John, please go ahead.
Good morning. Thank you, folks. So the history here is that Trevi Systems had been working for many years using a switchable solvent as a draw solution in forward osmosis, and we were delighted to see that Idaho National Labs had been working in parallel with us. So we formed a cooperative research and development agreement to create with them and have been working for the last year and a half on this technology, which we believe has great merit in removing hard ions from water. Next slide, please. So the process is fairly straightforward. We use a low-cost gas, dimethyl ether. It's being considered in the European Union as a gasoline substitute. It's also used commonly to extract vanilla essence and things like that, and is an FDA-approved gas, which has no greenhouse gas implications either. And we want to pair this with brackish water RO, EDI systems, etc., to remove these hard scaling ions, which ultimately limit recovery in RO systems. So this is a thermal approach where we're kind of joining because we believe there's tremendous merit in marrying these two technologies together. We inject the dimethyl ether into the saline brine stream from the RO plant. It can selectively precipitate out the hard ions. And by controlling the pressure on the system, we can control what precipitates and when. And then, of course, since it's a gas, removing it is relatively simple because we use solar heat to heat up the stream and the gas escapes. So from a process scale up, we believe this is a great way to go. We've done all the glassware together with INL experiments. We've moved to Aspen simulations, and now we're at a point where we need to choose the right technologies, right components to build a system. Next slide, please. So as you can see, there's it can pair with any existing desalination, whether it be RO, brackish RO, NF, EDI, etc. On the brine side, extract selectively the materials you want to extract. We have a program underway to selectively extract lithium, for example, as well. The key things under this program and the goals are to really understand the CapEx as you scale the system up. The operating cost, of course, the kilowatt hours electrical, and right now, early simulations between INL and we agree that it's around 20 kilowatt hours a cubic meter, which is remarkably low. And we'd like to see what the operating envelope is, how much salt at what pressure and what temperature can we extract. Overall water recoveries look very good, above 99%. So you actually end up with a salt slurry out of this process. Next slide, please. So I think what we need to do is find ourselves a solar thermal energy source. And so I notice there's a couple that have been on these pictures, and we'd like to partner with one of those folks. Temperatures are around 80 Celsius maximum, maybe 65, 70 would be fine as well. Choose all the system components, find a trial site as soon as possible, and then complete the licensing and other commercial agreements with INL. Next slide, please. And this is where you can contact me. We look forward to working with folks who are scaling this up for selective extraction of minerals. We believe this is one of the best ZLD technologies that we've looked at over the number of years we've had, since it's membrane-free and directly drops the salts out with almost total recovery of the dimethyl ether, basically less than 1 ppm in the permeate water. Thank you very much.
Thank you, John. Our next team is XVAP, self-contained distillation. And this is technology from Cat's Water Technologies in Houston, Texas. The team captain is Aaron Picton. Aaron, please go ahead.
Thank you. As he said, my name is Aaron Picton. I'm here today on behalf of Cat's Water Technologies to introduce our XVAP product, which is a mobile, self-contained solar thermal desalination system. We're here in hopes that some of you are inspired to join our team and support our mission of solving the world's water problems. Next slide, please. Some of the most glaring of these water problems in the world are within the oil and gas industry, producing millions of barrels of contaminated water daily. Specifically, produced water management accounts for 90% of water handling and disposal needs. Traditional injection wells cause a host of environmental issues from contamination to increased seismic activity. So we developed the first generation of the XVAP to fit in this market using natural gas as the thermal input to desalinate and treat water on site. And of course, now we are further developing the technology to run exclusively on solar thermal energy. Next slide. Okay, getting straight to the bottom line here, our system has many advantages as compared to our closest commercial competitor for quote mobile on-site water treatment. As far as footprint goes, our system fits within a small 6x12 trailer as opposed to a large crane site. As far as capital costs, we have a distinct advantage because all of the components of the system can be manufactured using off-the-shelf products with the exception of one custom part. And of course, the physical footprint comes into play here as well. And after the transition to solar thermal, there will be no energy bill associated with our equipment, which would drastically reduce operational costs. Next slide. So the enabling technology behind the XVAP system is the thermal distillation unit, which is a proprietary heat exchanger modification which uses pre-existing system energy to fully distill and purify water internally. So the three pieces you see on the right fit concentrically within each other and achieve multiple steps of the distillation process within a single vessel. 3 patents have been issued so far on this technology. We have many more filed and pending, 9 filed and 4 pending, I believe. Next slide, please. With help from an NSF SBIR phase 1 and 2 grant, we've been able to take this concept from paper to our first prototype test, shown on the left here, which took place in an employee's garage, to a fully operational natural gas powered trailer system, which you can see here getting set up for operation at a small oil and gas well site just north of Houston. Next slide, please. Moving forward, we are fully committed to the development of our solar thermal prototype and are currently performing lab tests with our brand new solar thermal collector. From a teaming standpoint, we would love to connect with any of you who have access to or expertise with either test sites, especially in non-oil and gas markets like agriculture or municipal water treatment. We're very interested in testing our equipment for PFAS and PFAS removal. So if you have a site that has PFAS contamination and would be willing to share your water samples, we'd be very interested to hear from you. Water and chemical testing, we're especially looking for PFAS capabilities there as well. And then of course, always interested in partnering with anyone in the manufacturing space, as far as prototypes or mass production capabilities. Finally, we are looking for a thermal engineer who would be interested in running simulations as we continue to develop this product. Next slide, please. So that's it for us. We hope to connect with all of you again next week at the networking event, but please feel free to reach out in the meantime. My email's up here, as well as our CEO and founder, Gary Katz. And be sure to check out our website at katzwatertx.com. Thank you.
Thanks, Aaron. Our next project is from Crystal Clear Water Resources, working on LTD technology. The team captain is Casey McKinney, and the team is based in Frisco, Texas. Please go ahead.
Okay, thank you very much. Good afternoon, everybody. My name is Casey McKinney. I'll be presenting on behalf of Crystal Clear Water Resources. CCR was established in 2015 to address some of the most challenging issues related to wastewater treatment across multiple industries. Our team currently includes members of CCR and TP Tech, Brent Halderson providing engineering consulting for this challenge, Chris Odland, information security, Marina Foster, the project manager for the Solar Desalination Challenge, Scott Carson, Vice President of Marketing for CCR, and Mark Lehman, who is the founder of Thermal Purification Technologies, and he is the inventor of the LT-DIS and LT-Dry technologies. Mark also has years of experience in developing leading edge technologies to treat challenging wastewater streams. We are also currently in discussions to add several other key team members shortly. Those include testing facilities, national labs, and commercially available solar thermal companies. Next slide, please. CCR proposes to integrate solar thermal collection into our existing low temperature distillation or LT-DIS technology. LT-DIS is a self-adjusting and adaptive process that can operate under a wide range of both full and partial load conditions. It's therefore able to maintain thermal balance despite the variability of the solar energy source. In critical applications where treatment needs to continue regardless of solar energy availability, conventional thermal power can be utilized to augment operations when adequate solar energy is not available. Our modular design allows us to scale plant sizes to meet client needs. In arid regions where high water stress and lack of brine disposal options, the combination of solar thermal energy with the LT-DIS process provides the ideal solution for sustainable water treatment. We believe that our process is ideally suited to be powered by solar energy. Next slide, please. Our goals include integrating solar thermal into our treatment process to be used as the primary heat source for operations during daylight hours. The utilization of solar energy as the primary heat source will decrease operational expenses as well as the overall environmental impact of the facility. We plan to optimize the LT-DIS process, including the integration of mechanical vapor compression with solar thermal heat source to lower the overall levelized cost of water below what is currently commercially available from traditional evaporative technologies. We also plan to explore cutting-edge solar thermal options that would enhance our technology even further. Next slide, please. Our action items include determining the solar field requirement needed to operate a 240 meter cubed per day LT-DIS plant, utilizing solar as the primary heat source for daytime operations. We must also ensure that our design allows for the integration of mechanical vapor compression, as well as secondary conventional heat source to allow for continuous uninterrupted plant operation at night or in suboptimal solar collection conditions. We will utilize internal process modeling to ensure safe, reliable, and efficient plant operations under any conditions. Next slide. That's my contact information there. Thank you very much for listening. If anybody has any questions or feel that you can contribute to our team, please feel free to send me an email or check us out on social media. Thank you very much.
Thanks very much, Casey. This brings us to our final presentation. This project is about 100% solar transcritical water desalination. It comes from Epiphany Solar Water Systems in Pittsburgh, Pennsylvania, and the team captain is Tom Joseph. Tom, floor is yours. Tom, you may be muted.
There, is my sound coming through now?
Yes, now you're coming through.
Still not?
No,
okay,
yes.
Good. All right. Sorry about that. Okay, so as John said, my company is called Epiphany Solar Water Systems. If we can jump to the next slide, please. We were founded in 2009, and the premise, the mission of our company is to help contribute to solving the world's water problem. And one of the core tenets or core, problems that we recognize from the very beginning is that if the entire world's population who needs clean water were to get their water using current state-of-the-art reverse osmosis, it would take all of the energy on Earth, all of the man-made energy on Earth, times 5 to provide the clean water that is required by everybody on the planet. So that's obviously not an option. And so we set out to find better, not just more economically efficient, but more energy efficient means to solving the problem. We've been doing this for 11 years now. We have several mechanical vapor recompression units in the field for the oil and gas industry. And we also have spent quite a bit of time doing R&D on multi-stage flash, solar thermal concentrators, as you can see in our picture there, and also very rudimentary technologies like submerged combustion, which have some application in the oil field. This project is a little bit more out there. Next slide, please. A little bit about our team. Again, I don't want to spend too much time on this, but basically we have a very highly qualified and experienced team working on this. And this is just a subset of our full team. Next slide, please. This is the important part. The premise of this particular project is that we learned that as water approaches its critical point, before you even reach the critical point and before there's any phase change, the solubility of inorganic salts drops to near zero. It's well under 100 parts per million, which is sufficient for drinking water. So the goal is to keep the water liquid, where you can do a very simple heat exchange. The challenge, obviously, is you have to operate at very high temperatures and pressures. We're talking, 750 degrees Fahrenheit, 3,500 PSI. That's not exactly a pleasant environment to work in, especially given the corrosive nature of the chloride-laden water at those high temperatures. Next slide, please. For our prototype, we've already done some 3D modeling, some math modeling, and fluid dynamics modeling. We're very confident that we're going to be able to build a functional prototype that'll process water for less than 10 cents a gallon. That's not much of a goal. That's still really expensive, and we know it. But for a prototype, it's not that bad. We think we can take one to production for around 3 cents a gallon, and that's just very early initial production. Our goal obviously is to get much less than that, something like 1/10 of that. But we think the market will accept something in that range, at least certain markets. We're talking disaster relief and military use, things like that. But then obviously, as we really want to go out and start solving the third world country problem where people need this the most, that price has to come way down, and it will. Next slide, please. Pretty simple, action items and goals here. Like everybody else, our goal is to have everything done by the end of January. So we're going to complete the design along with bill of materials, get the process flow diagram finalized, mass balance. Most of this is already done. We just need to put finishing touches on a lot of it. We'll finalize performance metrics for our prototype so that we have to define what success looks like. We'll develop our commercialization plan, which is already underway, and then we expect to be able to submit the whole package by early February, along with everybody else. Next slide, please. The biggest lack of expertise, or where we could really use some help here, is because of the high heat and pressure required for this type of system. We could really use some help with anybody who has experience building pumps and delivery systems and measurement systems for that handle that kind of those kind of conditions. And then, of course, if there's anybody out there with any expertise in transcritical or supercritical process engineering, that's sort of a world of its own within water. Not that many people deal with supercritical water. So if anybody's out there who is willing to help us with that, we would love to talk. Next slide, please. Mike Broker is our point of contact. That's who you'd be reaching out to. You can always find me. I'm Tom Joseph, and my email address is the same as Mike's there, but it's just tom@EpiphanySWS. So feel free to reach out to either of us, and we'd be happy to hear from any of you. Thanks.
Thank you, Tom. And thank you to all of our 19 teams who attended today and presented. I think you can see from the range of creative and innovative ideas that have been shared that there is quite a lot happening around thermal distillation, thermal desalination, and we certainly should expect to see that technology continue to move forward over time. For those of you who are getting to the point of publishing your research, I'd like to point out that the IDA will have its World Congress on Desalination and Water Reuse in Sydney, Australia, in November 2021. And our call for proposals will remain open until about February 1st. So we'd all love to hear more about the work you're performing. And please do consider sending a proposal or an abstract into the conference. You can find the link to the Congress in the chat. And I would encourage all of you to give it a shot. So thank you very much. And I will wrap up here.